Hello, this is Rahul here, back again from MySlate. In this session, we will look at some applications of derivatives, and we will begin by looking at how we can express the rate of change of quantities using the notion of derivatives. There is a rectangle which we have drawn here, and it has a certain length and certain width at a given point in time. But its length and width are changing with time. So, as the problem says, its length is decreasing at this rate, 3 centimeters per minute. Every minute its length shrinks, and the width is increasing, the width is expanding at a certain rate, 2 centimeters per minute. So the length and the width are not same at different points in time, they are changing. So, the question is that at the time when x is equal to 10 centimeters and y is 6 centimeters, that is what is shown here. At that moment of time, what is the rate of change of the perimeter of this rectangle and the area of the rectangle? Right? So, you would probably intuitively understand that because the length is changing with time continuously and the width is changing, the perimeter and the area would not remain the same, they would also change, and we are asked to calculate that at the moment when x and y are at certain levels. Okay, so let's try to solve this problem. So first of all, you need to apply the signs correctly. So it is let's call length x and width as y. So it's given that the length is decreasing with time. So therefore, dx by dt should be negative. We have already seen earlier that this implies negative slope of x with respect to time, and we represent that by a negative value of the derivative. So that's minus 3 centimeters per minute, and the width is increasing with time at the rate of 2 centimeters per minute. So that would be positive. Now let us express the perimeter in terms of x and y. Now you probably already know that the perimeter of a rectangle would be 2 times length plus 2 times width, and here all the units are in centimeters. So we make a note of that the perimeter is also in centimeters. So perimeter here is the total length of the boundary of the rectangle, which is 2x plus y. So we are asked to calculate the rate of change of perimeter with respect to time at the moment when x is 10 centimeters and y is 6 centimeters. So let us first try to get a general notation for the derivative of perimeter with respect to time, and then we will plug in the values x is equal to 10 and y equals 6 in that. Okay. So what would be dp by dt? This is what we are asked to calculate. So this is the rate of change of perimeter with respect to time, and we already know that the perimeter is 2 times length plus 2 times width. So dp by dt is the d by dt of that, and we already know from the earlier discussions that derivative of the sum of two functions is the sum of the derivatives of those two functions. So we can split these two terms here, and the constant can be taken outside as a multiplying factor. So this becomes 2 times dx by dt, which means 2 times the change in the length and the rate of change of length plus 2 times the rate of change of width. And we plug in those values of dx by dt, which is minus 3, and dy by dt, which is plus 2, and we get dp by dt as minus 2 centimeters per minute. So what that implies is that the perimeter is shrinking, is decreasing at the rate of 2 centimeters per minute at the time when x, well, here you see that dp by dt is a constant number, minus 2. It doesn't matter what the value of x and y is. There is no x and y in the expression for dp by dt. So that means dp by dt is constant no matter what the value of x and y is. So whether x is 10 centimeter and y is 6 centimeters, or even at other moments when they take different values, dp by dt always is minus 2 centimeters per minute. So the perimeter is always shrinking at any point in time, and also at the time when x is 10 and y is 6. Let's see what happens to the area. Now, we already know that the area of a rectangle is length times width, and the unit here would be centimeter square. So, therefore, what would be dA by dt? The rate of change of area with respect to time. So, we have to calculate d dt of xy, and we can apply the product rule of derivatives, which means the derivative of the first term multiplied by the second term plus the first term multiplied by the derivative of the second term. And we know that dx by dt is minus 3 times y plus x times dx dy by dt, which is plus 2. And we get this time an expression for dA by dt, which is a function of x and y. So, unlike dp by dt, which was a constant no matter what the value of x and y is, dA by dt is not a constant. It depends on the value of x and y. And we know that because x and y change with respect to time, the rate of change of area with respect to time would be different at different points in time. And we have been asked to calculate that at the time when x is 10 centimeters and y is 6 centimeters. So, therefore, all that we need to do is plug in those values here, and that is what we have done here at the bottom. So, we write it as dA by dt in square brackets, and as a subscript we say we indicate the point at which we are expected to calculate that. So, that is at when x is 10, y is 6, and we plug in those values and we get plus 2 centimeters square per minute. That is the rate of change of area. So, plus 2 centimeters square per minute, what would that imply? That the area is expanding. So, that is very interesting. While the length is decreasing at the rate of 3 centimeters per minute, and width of this rectangle is increasing at the rate of 2 centimeters per minute, the perimeter is always decreasing at the rate of minus 2 centimeters per minute, whereas the area of the rectangle at a particular time when x is 10 centimeters and y is 6 centimeters is increasing at the rate of 2 centimeters square per minute. But please note that the area would not be changing at a constant rate of 2 every time, because we have already seen that dA by dt is a function of x and y, right. So, it is possible that there are moments in time when area is decreasing. It just so happens that at this particular time when x is 10, y is 6, the area is increasing even though the perimeter is decreasing. Okay, so with that simple example, I hope you appreciate that this notion of derivative is quite powerful, and we can use it in real world to calculate the rate of change of physical quantities of the kind whose examples we saw in the previous slide. So, I will see you now in the next video with other applications of derivatives. Okay, see you then. Bye.